Well, hi there. I hope that you're all doing very well and are excited about today's class. I know I am. I am your personal physics tutor, Dr. Rima McMullen, and I welcome you to today's class on one-dimensional motion, aka also known as motion in a straight line. Now, before we start today's class, I hope that you all have your notebook and pen ready to write down your notes. Now, you might ask, why do we have to write down notes? All kinds of textbooks are available there. There are so many websites, there are PDFs floating around. Now, there's even artificial intelligence that can generate all sorts of notes for us. So, it doesn't seem like we really have to write down our own notes. But we really do. There are several benefits of writing down notes, and some of the benefits are, for example, we learn new information by interacting with it with our senses. Some people learn best by hearing the information. They're auditory learners. Some people learn the information best by seeing it. They're visual learners. And some people learn it best by doing it. And they're tactile learners. So the more you get your senses involved in learning, the more you're going to learn, the more you're going to understand. Therefore, by writing down, when you're taking down notes, your tactile sense is also getting involved. You're enhancing your active engagement with the content, with the subject. And what that does is that improves your attentiveness and your focus, and hence your understanding and your retention of the subject. So hopefully now you understand the importance of writing down your own notes. I mean, you don't have to write down every single word that I'm saying, but the important things, important points, you definitely want to write them down. All right. With that being said, now we should start our today's class. Let's see what today's class is about. Like I said, today's class is on one-dimensional motion. We're going to devote this class to developing a basic understanding of the one-dimensional motion. I'm sure you're already familiar with quite a few concepts of one-dimensional motion. We're going to dig deeper into it today. We're going to look at what is motion, what is kinematics, what is dynamics, what is a frame of reference, how many kinds of frames of reference are there. We're going to look at different definitions such as distance, displacement, speed, velocity, acceleration, and subtle differences between them. For example, acceleration. We're going to look into what does the sign of displacement, velocity, and acceleration mean. How are they related to each other? There's typically a lack of understanding among students, typically regarding acceleration. So we're going to dig deep into that today. Now, since the topic for this class is one-dimensional motion, the very first question that we're going to tackle is, what is motion? Motion is defined as change in position with respect to time. Let's talk about my position at this instant of time. At this instant of time, I'm sitting in my office chair in my home office. As long as I do not move myself or the chair, I say I'm at rest. But here's the question. What am I at rest with respect to? I am at rest with respect to the walls of this room. I am at rest with respect to this house. In fact, I am at rest with respect to everything that is on this earth. But am I really at rest? Well, if you were an alien watching me from a different planet, would you find me at rest? No, you would not find me at rest. You will see that I am on Earth, and the planet Earth, it is orbiting around the sun with a whopping speed of 30 kilometers per second. That's pretty fast. And Earth is not only revolving about the sun, it's also spinning about its own axis. And its speed of rotation about its own axis is 465 meters per second. And not just that, Sun itself is spinning about the center of Milky Way galaxy. Why? Because at the center of every single galaxy, there is a massive black hole, which makes everything in the galaxy spin about it. And not just that, the Milky Way galaxy itself is going through space at the speed of 600 kilometers per second, which is 2,160,000 kilometers per hour. Not just that, the universe itself is expanding. And at places, the speed of universe's expansion, it exceeds the speed of light. Now, this was the discussion of motion at large scale, at astronomical scales. How about motion at very, very small scale? At very small scale as well, there is always motion. For example, the air around us, the gas molecules, they are constantly bouncing off of each other, and this kind of motion is called as Brownian motion. Even the atoms in solids, they are also moving. They are moving at every single instant of time. And the motion of the atoms, it's a measure of the temperature. The higher the temperature, the faster the atoms would move. They are moving about their equilibrium position. So it's safe to say that everything in the universe is in a constant state of motion. Everything is constantly moving. There is no such thing as absolute rest. But the question remains, what is it moving with respect to? For example, let's look at the scenario. I'm sure you agree that this car here, it's moving to our right. But talk to this little guy wearing green shirt who's saying that, the car's moving to the left. And this other kid on the other side of the road wearing this orange shirt, he is saying, nope, the car's moving to the right. Which of these two kids is right? Are they both right? Are they both wrong? Well, they couldn't both be right. The car is going to move only in one direction. It can't be going to the right and to the left at the same time, could it? So the answer is that both of these kids are correct in their own respective frame of reference. So what is frame of reference? Speaking in simple terms, a frame of reference or reference frame, it is a coordinate system. It's a grid of reference points, a background against which motion is measured. Frame of reference, it can be of two kinds. It can be inertial or non-inertial. Now, what's the difference between inertial and non-inertial frame of reference? An inertial frame of reference is the one that is moving with constant velocity. Now, mind that zero is a constant. So if an object is moving with zero velocity, that means it is at rest. We can still claim that that object is moving with constant velocity. Why? Because zero is nothing but a constant. Alright, so that is the definition of an inertial frame of reference. How about a non-inertial frame of reference? By contrast, if inertial is moving with constant velocity, a non-inertial reference frame should be moving with what? Non-constant velocity, a variable velocity. In other words, it should be accelerating. I know I have not yet defined what is velocity and what's acceleration, but I'm pretty sure that you already have at least some idea of what is velocity and what is acceleration. But if you don't worry, we're going to devote this entire lecture studying these concepts. We're going to go into deep details of these concepts. For now, though, let's move on to the next slide and talk about a few very familiar frames of references. The first one, Cartesian coordinates, regular x, y, and z coordinates, where these x, y, and z axes, these are related to each other by what? Right hand. So to go from x to y, point your fingers along the direction of x. Okay, so let's say, hang on, this pen here, this black tip, this is the direction of x-axis. So you're going to point your fingers, right hand fingers, in the direction of x-axis, wherever you're choosing the x-axis direction to be. Then you're going to curl your fingers inward. Okay, so I'm curling my fingers inward toward my palm. And at some point you will see that my fingers and my palm, they are at right angle to each other. So the direction of my fingers, this is the direction of what? This is the direction of y coordinate. The pen here with its flat tip, that is the direction of x-axis. This is y-axis. And my thumb, it's pointing away from my hand. This is going to be the direction of z-axis. So the x, y, and z coordinates, these are mutually at right angle to each other. And to go from x to y, you're going to point your right hand fingers in the direction of x, curl it toward y, curl your fingers inward toward the palm, and until the fingers are pointing at 90 degrees to your palm, and point your thumb away from the hand. And the direction of your thumb will be the direction of z-axis. Same way you could go from y to z. Point your right hand fingers along the direction of y-axis, curl them toward the palm, and the direction of your fingers when it is at right angles to the palm will be the direction of z-axis, and your thumb will now point in the direction of x-axis. Likewise, if your right hand, when it is flat like this, your fingers are pointing in the direction of z-axis, curl your fingers in toward the palm. When your fingers are at right angle to the palm, that would be the direction of x-axis. Your fingers are pointing in the direction of x-axis, and now your right hand thumb, that would give you the direction of what? Y-axis. Alright, so that was that about the Cartesian coordinates. Next thing, do we have any other kind of coordinate system? Now tell me, have you heard about any other kind of coordinate system? If you have, please do let me know in the comments. I'm curious to know which kind of grade level you're at. Maybe you're in college, maybe you're in high school. Do let me know where you're watching from, what level you're at, and if you have already heard about spherical polar coordinates. Depending on the symmetry of the problem, many times we're going to use spherical polar coordinates instead of using Cartesian coordinates. And at other times we're going to use cylindrical coordinates. Again, have you heard about cylindrical coordinates before? I'm not going to show you here how spherical polar coordinates look like and how cylindrical coordinates look like. I will make an entire video on that. And we'll be using spherical polar coordinates and cylindrical coordinates when we work on electricity problems. Alright, for now, let's see what the next slide says. Next, what is needed to be done to study motion? Now, motion is the change in the position with respect to time. So somebody or something, maybe a tool, maybe a machine, needs to observe that position is changing with respect to time. So an observer is needed to study motion. What else is needed? You need a coordinate frame. If the position is changing, it is changing with respect to what? So a coordinate system is needed to tell if there is motion. Lastly, since it is change in position with respect to time, how do you measure time? Using a clock. So you need a clock to measure motion. We are now going to look at some terms. The first term that we're going to look at is kinematics. What is kinematics? Kinematics is a branch of physics. It is a branch of classical mechanics, to be precise. It studies how of motion. It doesn't care about why of motion. It doesn't care why motion is occurring. It cares only about what kind of motion is occurring and how it is occurring. Meaning, what does it mean? It means that how far did an object move? How far did it travel? It will care about how fast it is going. Did it speed up or did it slow down? And how long did it travel for? How much time did it take? So all these things, they are studied in what? They are studied in kinematics. So like you're seeing here, it doesn't care about why an object is moving in the first place. All it cares about is, okay, so it's already in motion. How far is it going? How fast is it going? Does it speed up? Does it slow down? And how long did it travel for? Next term that we're going to look at is dynamics. Dynamics is, again, it's a branch of physics. It's a branch of classical physics that deals with why do things move. If an object is moving, what caused it to move? Was it pushed or was it pulled? Because an object sitting by itself is not going to move. Something has to make it move. There has to be a force that acts on the object that makes it move. So that is going to be studied in what? That's going to be studied in dynamics. So if an object is being pushed or pulled, that is, a force is acting on it. Did it slow down? For example, maybe friction caused it to slow down. Or maybe the object sped up. For example, if an object is falling downward, gravity is going to cause it to speed up. So dynamics is basically all about the forces that cause motion or they change its state of motion. So we can say that dynamics, it deals with what? Newton's laws. So Newton's laws, they come into play where? When we study dynamics. But when we are studying kinematics, Newton's laws have nothing to do with it. So this chapter, all the lectures in this playlist, they are going to be based on kinematics. Newton's laws, that is dynamics, we're going to do in a later chapter. Like I already mentioned, all the lectures in this playlist, they are going to be devoted to what? They are going to be devoted to kinematics. And we said that kinematics is a branch of physics. It's a branch of classical physics that deals only with what? How of motion. What is occurring in the motion? And it does not care about why of motion. Not of here, does not care about. It doesn't care about what? It does not care about why of motion. Okay. So in this, we are going to study what we call as translational motion. What is translational motion? Translational motion is, it's the kind of motion where all parts of a body, they move in the same direction and with the same speed. For example, let's say you are at a park and here is a slide here. And when you see a child coming down the slide, all parts of the child, they come down with the same speed. They all come down in the same direction. So this child is undergoing what kind of motion? He or she is undergoing translational motion. And to study translational motion, we're going to treat an object as what? As a point object. Why do we do so? It is done to simplify calculations. That is the purpose of treating an object as a point object, to simplify our calculations. Now you know that physics, it's a combination of concepts and mathematics. And what do we do in mathematics? We have to do calculations. So physics, a lot of it has to do with what? Calculations. And we want to do whatever we can to make our calculations easier. Why? Not because we don't want to be able to do difficult calculations, but because the easier a calculation is, less likely we are to make an error, and we want to reduce our errors. Therefore, we want to simplify calculations. And besides, in some of the real life things, in some of the real physical things, things can be so extremely complicated that it is impossible to carry out their exact calculation. And in those cases, you do have to make approximations. And one of the approximation is what? Treating an object as a point object. Let's now see, what does a point object mean? A point object, like I already said, we're going to treat an object as a point object only for translational motion. And what is translational motion? Where every single part of a body that is undergoing motion is moving in the same direction and with the same velocity. Well, when I say same velocity, it implies that it's same direction. I should say same direction, same speed. Why I'm doing that, why I'm saying that way, you will see in a few minutes. So, another condition for treating an object as a point object is that the distances covered, they are very, very large as compared to the size of the object. Okay, that was pretty easy to understand. So a point object, it is an idealized object with no shape and no size. So even though a point object, it is an object with no size, no shape, it still possesses all the other properties of the object. What kind of properties? It will still have mass. Therefore, it will have momentum because momentum is mass times velocity. It will have charge. It will have spin, etc., etc. All these kind of properties, they are still possessed by the object, by the point object. What is next? Aha! So, a point object, it is that point where all of the mass of the object was concentrated. So, center of mass of an object, it is actually a real physical geometrical location inside the object where all of the mass can be pretended to be concentrated. So in case if all of the mass of the object, of an extended object, it was somehow squeezed into this one spot called the center of mass, then that point object with all the mass at the center of mass is going to behave the same way as the extended object itself does. So that is the definition, kind of a rough definition of center of mass. We're going to get into technical definition of center of mass in a later chapter. For now, you kind of just want to have an idea of what is center of mass. You don't really need to know more than this. Not for now, at least. So, we said that so far, that this chapter, this playlist, it is devoted to kinematics, where we study only how of motion. We do not care about the forces that are causing the motion. We care about those forces where? In dynamics, which will be the topic of another lecture, another chapter. And then we said that in kinematics, we are going to treat the objects that are undergoing motion as point objects. And it can be done only when the object size is very small as compared to the size that it is traveling. All right, what is next? What is on the next slide? Let's see. We are now going to go over some definitions. The very first term, distance. I bet you're all familiar with what is distance. I mean, we all have an idea of what distance is. Let's look at an example. Let's say you are starting from your home. Your home is right here at 0. And you go to your friend's place that is located right here at 3. This is your friend's place. What's your friend's name? Let's call your friend Sam. To get the distance between your home and Sam's house, you can divide the path into small segments. Very, very small, straight segments. And then add them all up. When you do so, what do you get? You get distance. Right? This is how you will get distance. Here we go. Okay, I know there's no point trying this, but it's too much fun. I can't stop. Okay, so here, let's say the distance traveled is, let's call it as x, yx because this is one dimension. So let's stick with one dimension. And even though this dimension could be x-axis or y-axis, let's stick with x-axis. The distance traveled, it will be sum of all these segments, xi. In this case, each of these segments is identical in length. However, in general, you could have a distance traveled, like this. In this case, you're starting here, let's call it O, and then A, B, C, and D. You're traveling in a straight line from O to D. And as you can see that these length segments, OA, AB, BC, and CD, they are not identical in length to each other. So here, OA could be x1, AB is, let's say, x2, BC is x3, CD is x4. So the distance traveled will be x1 plus x2 plus x3 plus x4. You can write this as a summation over xi, where I is running from 1 to 4. What it means is that xi, first take I to be 1, which gives you this over here, x1. Then you go to x equal to 2, add that. Then you move on to x equal to 3, add that. And the last one is x4, so you go till x4. This is going from I equals 1 to n, where n is the number of length segments that are being added. So this is your definition of what? This is definition of distance. So distance is the sum of all the path lengths. And once again, the formula will be x equals summation over xi, where I goes from 1 to n, and n is the number of length segments. Okay. Now, what kind of quantity is distance? Is it a scalar or is it a vector? Well, what is the difference between scalar and vector? A scalar is a physical quantity that has only magnitude and no direction associated with it. So distance is a scalar quantity. Next, what is the SI unit of distance? The SI unit is meter. Now, meter is abbreviated as lowercase m. Now, I don't know where you're watching this video from. In American English, meter is M-E-T-E-R. In British English, it is M-E-T-R-E. They're both correct in their own countries. In either case, the abbreviation is lowercase m. Now, physics and chemistry, these are very, very case-sensitive subjects. So you absolutely cannot use uppercase m for meter. You have got to use a lowercase m for meter. Okay, now this is SI unit for distance. Other than SI unit, you have several other units to measure distance. For example, foot, yard, miles, light year, etc., etc. There are quite a few of them. So this is your distance. What is our next term? Next term is displacement. So what is displacement and what is the difference between distance and displacement? Displacement is a straight line, the shortest distance that connects the initial and the final position. Okay, so in this case, the initial position is 0 and the final position is 3. So we're drawing this straight line with an arrowhead going from 0 to 3. The direction of the arrowhead, it tells us the direction in which the travel is taking place. And because of this arrow over here, displacement is a vector quantity. Unlike the case of distance, which was a scalar quantity. The SI unit of both distance and displacement is meters. Now the displacement over here, since it is a straight line between the initial and the final position, it is going to be the shortest distance that connects the initial and the final position. Now, working in one dimension and saying that this one dimension is along the x-axis, displacement is going to be delta x with an arrow above it. This arrow implies that it is a vector quantity. It is equal to xf, which is final position along the x-axis, minus xi, which is the initial position along the x-axis. If you wish, you could write this as x minus x naught. Here x naught is the initial position and x is the final position. So this is the formula for what? This is the formula for displacement along x-axis. This is one-dimensional displacement only. In three-dimensional, formula is slightly different. We're going to do that in another chapter. Once again, the formula for distance was summation of all the line segments where I goes from 1 to n is the number of different line segments that are being added together to give you the distance. Let's now look at an example to understand the similarity and dissimilarity between distance and displacement. Can these two quantities ever be equal to each other? If yes, under what condition they will be equal to each other? And under what condition could they be different from each other? And in case if they're different from each other, is one always going to be greater than the other? Let's see. So in this example, you're going to go from your home, that's over here, to the grocery store. So you can see that in this example, your home and the grocery store, they both lie along the same street. And to go from your home to the store, you come across not just one, but yeah, 3 lights. There are 3 lights on the way. And as luck would have it, when you're driving from your home to the store, every single light is going to be red. So you start from your home, you drive along this green line, and you get to first light. Let's say the coordinate for the first light is x1 and the coordinate for your home is xo. So the distance traveled here, let's call it as d1. What would be d1? Not d1 actually. Let's call it as, yeah, d1. d1 is fine. d1. d1 is the distance traveled between x0 to x1. So you park here for a minute or two, whatever, and then you go from x1 to x2 when the light turns green. But then again, when you reach this second light, the light is red again, and you have to stop. Between x1 and x2, you travel a distance of d2. And when the second light it turns green, you drive along this pink line until you reach the third light, which is again red. So you stop over here, and between d2 to d3, you travel the distance d3. When the third light turns green, you travel along this blue line, and you travel the distance d4. So your distance traveled will be what? d1 plus d2 plus d3 plus d4. And that's going to be this entire distance over here. All of this distance. What would be your displacement? Displacement will be final position, which is x4, minus initial position, which is x0. And let's put these arrows. So if you talk about the magnitude here, the magnitude of the displacement, which is x4 minus x0. So this case, when you're traveling along a straight line without any reversals, your distance and your displacement are same. But, yep, there's always a but. In case you get to the store, okay, and then you realize, oops, I left my wallet at home. You have to turn around. You have to go all the way back to your home, grab your wallet, and then come to the store. Now, in this case, where you went to the store, you made a U-turn, you came back, and then you went back to the store again. What would be your distance traveled? Traveled will be 3 times of this distance, correct? You traveled the same distance, d1 plus d2 plus d3 plus d4. How many times? 3 times. So 3 times d1 plus d2 plus d3 plus d4. Let's not talk about what? Displacement. Yep. So we know that displacement is what? It is a vector quantity. And in this case, let me remove this arrowhead. So this is your first travel, second, and third. So you can see that the first and the second, or if you want the second and the third, they are in opposite directions. So 1 is along positive x-axis, 2 is along negative x-axis, 3 is along positive x-axis. So when you add up these displacement, you can say that 1 and 2, they cancel each other out, correct? And remaining one is just the third. If you want to be more technical, look at this. Let's find the displacement for the entire trip. Okay, where are you starting? You're starting at x0. Okay, what's your final position? x4. First time you went from x0 to x4, and then you returned from x4 to x0, and then you went back from x0 to x4. So over here, x4. This is your final position, and initial position is x0. So your displacement will be x4 minus x0. It did not change, did it? If you want to be, more technical and do the entire math, say this. Your first trip, the displacement is x4 minus x0. To that, add the displacement for the second trip. In the second trip, your final position is x0. You're going back home. And your initial position was x4. You started from the grocery store. Then you're returning to the grocery store. You're starting at x0 and you're going to x4. x4 minus x0. Now these are vector quantities, and you see that minus x0 plus x0 cancel out. Not just that, plus x4 minus x4, they also cancel out. You're left with x4 minus x0 at the end. So you can see that in the case when you travel along a single straight line with no reversal, distance and displacement, they are equal to each other in magnitude. But if you travel in a single straight line with reversals, in that case, the magnitude of distance is greater than the magnitude of displacement. So over here, let me insert a new slide. All right, so we considered two scenarios here, right? Case 1, in which you did remember to bring your wallet, okay? You traveled a distance d1 plus d2 plus d3 plus d4. And in that case, your displacement is equal to x4 minus x0. And the magnitude of this displacement is equal to d1 plus d2 plus d3 plus d4, right? Then there is this case 2. Let's write case 2 in blue color and case 1 that was in white color. Okay. In case 2, the distance traveled is going to be what? Just like we said on the last slide, 3 times d1 plus d2 plus d3 plus d4. This case 2 is the one where you forgot your wallet at home. Okay. All right. I see that I need to move it over. All right. Now, in case of displacement, for the second case, we said that it is still equal to x4 minus x0. So this is the displacement in case of the second case, which is same as that in case of the first case. And its magnitude is still equal to d1 plus d2 plus d3 plus d4. So I hope you can see that distance equals displacement when you travel along a single straight line without any reversals. When you travel along a straight line without any reversals. However, in case where you choose to return, where you choose to come back, in that case, distance is going to be greater than displacement. So in general, distance is going to be greater than or equal to displacement, them being equal only and only when you travel along a straight line without any reversals. Okay, now let's go ahead and dig a little bit deeper into this. So you're going from home to store, okay? And over here on the other side of the road, your friend Sam, he lives. His house is over here. Your house is above the road here, as you're seeing on the screen, and Sam's house is below the road. And you want to pick Sam up on your way to the store. To do that, first you have to go to the second light and then make a U-turn to come back to Sam's house. And then you have to go all the way to the first light and then again make a U-turn and go to the store. So you see what I'm saying? So you're starting from your home, x0, you go to x1, you go to x2. Then you make a U-turn to pick Sam up. And then you go back to x1, then to x2, then to x3, and then to x4. What is your distance traveled here? D1, then you went to D2, then you came back along D2, then you went back along D2, correct? So D2 is traveled not just once, but 3 times, plus D3, plus D4. This is your distance traveled. But to go from your home to the store for that entire trip, what would be your displacement? Aha, that's again going to be x4 minus x0. Why? Because this going from 1 to 2 and then coming partway back to pick Sam up and then going to 1, these two displacements, 1 to 2 and then 2 to 1, they cancel each other out. And then you go again from 1 to 2, 2 to 3, 3 to 4. Of course, you had come from your home to 1 as well. So your displacement is D1, D2, D3, D4. That's the magnitude of the displacement. And you can see that in this case, distance is greater than displacement again. So I hope this makes the difference between distance and displacement clear. All right, let's move on to the next topic. We are all familiar with speed. Speed gives us an estimate of how fast we're traveling. But what is the formula for speed? The formula for speed is distance traveled divided by time taken. Now distance, is that a scalar or a vector? We just said distance is a scalar. How about time? Is that a scalar or a vector? Time is a scalar as well. So the quotient or the ratio of a scalar and a scalar is going to be what? A scalar. So speed is a scalar as well. Now let's talk about the SI unit of speed. Distance is SI unit is meter. Time is seconds. So the SI unit for speed is what? Meters per second. What is this? This is speed. Next we are going to move on to velocity. Velocity is displacement divided by time taken to make that displacement. So we can write speed as S, let's call it just S, x divided by t. X is the distance traveled and t is the time taken to travel that distance. Velocity, call it v with an arrow over it. Arrow represents that it is a vector quantity. Now, why is velocity a vector? It is because displacement we just learned it's a vector quantity. So vector divided by a scalar is a vector quantity. Velocity is going to be x final position along x-axis minus initial position along x-axis. That is the displacement divided by tf minus ti. Now, xi is the position at time ti and xf is the position at time tf. If you want, and for most practical purposes, we can say that when we start measuring the time, we start our stopwatch. And the stopwatch is going to begin at what? 0 time. So ti can be called as 0 time. And tf, just to make things easy, call it t. So velocity can be written as xf minus xi divided by t. And once again, what is the SI unit for velocity? Displacement is meters, time is seconds. So SI unit is meters per second. Now between speed and velocity, which one is going to be greater? What kind of equality or non-equality sign will hold? Now remember, we are dealing here with one-dimensional motion. Not that things will change a lot going from 1D to 2D or 2D to 3D. But let's stick with 1D for now. For 1D, we said that distance is going to be, okay, hang on, let me get rid of some of this from here, make some room to write. We said that distance is greater than or equal to displacement. This is the inequality or the equality that always holds between distance and displacement. How about if I divide both by time? Then what do I get on the left side? Distance divided by time is speed. Displacement divided by time is velocity. Now what you do is take the sign and bring it down. So you get that speed is going to be always greater than or equal to velocity. They are going to be equal only when the object is traveling in a single straight line without any reversals, without making any U-turns. So here we have distance, displacement, speed, velocity. Distance scalar, displacement vector. Speed scalar, velocity vector. Distance and speed, both with SI unit of meter. Speed and velocity, both with SI unit of meters per second. Distance is always going to be greater than or equal to displacement. Since speed is distance divided by time and velocity is displacement divided by time, therefore speed is always going to be greater than or equal to what? Velocity. Alright, next we are going to look at what is instantaneous speed and instantaneous velocity. Instantaneous means at a specific instant of time. At a specific instant of time. So to find it, what you do is that, so what we're saying is that velocity, it is delta x divided by delta t. Just to make things a bit easier, how about we do not write this arrow for now, just for now. We know that it's supposed to be there. We're just choosing not to write it to make life easy. What we're going to say is that this time interval, make it very small, okay? So we're taking the limit in which time delta t goes to 0. So we're making this time interval infinitesimally small, okay? That's what it is called. Infinitesimally small time period. Under this condition, what happens is that this delta x over delta t, delta x we know as delta means change. Delta x means xf minus xi. This changes to what? A derivative, dx over dt. And if we had xt graph, then this derivative, what it does is it represents slope of the graph, slope of xt at t, at the instant of time at which we're interested in finding the instantaneous velocity. So in simple words, instantaneous velocity, it is the slope of the xt graph at the instant of time where you're interested in finding the instantaneous velocity. Once again, instantaneous velocity, it is nothing but derivative of position with respect to time. And if you have the plot, the graph of x versus t, position versus time, then at whichever instant of time you want to find instantaneous velocity, find the slope of the graph at that point. And the slope of that point is equal to what? Instantaneous velocity. So what about instantaneous speed? It turns out that instantaneous speed is same as magnitude of instantaneous velocity. Here we go. So this is your instantaneous speed. All right. Now we know the difference between average speed, instantaneous speed. Average velocity, instantaneous velocity. What are we moving on to next? Let's see. Acceleration. Cool. Acceleration is written as lowercase a. What is defined as? It is defined as change in velocity, Vf minus Vi, divided by time taken to make this change in velocity. So that is Tf minus Ti. Now V, velocity, is a vector. Vector divided by scalar is going to be a vector quantity. So acceleration is a vector quantity. This can be written as delta V divided by delta T. This is in fact average acceleration between time Ti and Tf. So it is average acceleration during the time interval Tf minus Ti. How about instantaneous acceleration? Is there anything like instantaneous acceleration? Sure is. Instantaneous acceleration. So just like how we found instantaneous velocity, we're going to find out instantaneous acceleration. What we're going to do is we're going to take limit as delta t goes to 0 for this equation over here. Delta v divided by delta t. This changes to dv over dt. And this is nothing but instantaneous acceleration. So the derivative with respect to time of velocity function is called as instantaneous acceleration. Or if you had vt graph, then in that case, at whichever instant of time you're interested in finding the instantaneous acceleration, find the slope of that point. How we find the slope? We're going to learn that very soon. Okay? We're going to learn that in this chapter, just not here. Okay? So slope at point T. That gives you instantaneous acceleration at that specific time T. Okay, so this is acceleration. Next, what is the SI unit for acceleration? Let's see. We have change in velocity. Just throwing some numbers. Let's say it is 5 meters per second minus 2 meters per second. Final velocity minus initial velocity. What would this be equal to? 5 meters per second minus 2 meters per second. 5 oranges minus 2 oranges. 3 oranges. 5 meters per second minus 2 meters per second. 3 meters per second. Okay. Divide this by the time. Let's say it took the object 3 seconds. 3 seconds minus 0 seconds to go from 2 meters per second to 5 meters per second divided by 3 seconds. What happens now? 3 meters per second divided by 3 seconds. What do? Second cancels. I get 3 meters, correct? No. Meter is the SI unit for distance and displacement, and acceleration is not equal to distance or displacement. This is a common mistake that unfortunately several students do. So look at this. This is important here. Meter per second divided by second. What is this equal to? You have a very, very bad looking pie. Okay. You have only half of this pie. Okay. Now, out of this half of the pie, you eat another half. Okay. So this much is gone. What are you left with? You're left with this portion over here. This portion is left. So you had one half, the top half of the circle, then you ate the blue part also. So half of half is gone. If I cancel these two, I'll have one whole left. But I don't really have whole pie left. I have only a quarter left. That means, what does that mean? This is actually equal to 1/2 times 1/2. So this denominator Dividing by something is same as multiplying by its reciprocal. So 1/2 is being divided by 2. I can say that 1/2 is being multiplied by reciprocal of 2. Same way over here. Meter per second is divided by second. I can say that this meter per second at the top, it is being multiplied by reciprocal of second. So this gives us meters per second squared. Meters per second squared is the SI unit for acceleration. I hope this made sense. This is something that a lot of students somehow, for some reason, they have hard time understanding. I hope I did a good enough job at explaining it. If for some reason you think that it was not clear enough, please do let me know and I'll make another short video of showing how to get the SI units for acceleration. Okay, moving on to what? Deceleration. Acceleration versus deceleration. Okay. Deceleration is also called as retardation. And it has only one meaning, and that is slowing down. Now, unfortunately, I have seen quite a few other videos and I have read in some books as well saying that deceleration is negative acceleration. It can be, but it is not necessary. Deceleration, all it means is slowing down. It's not necessarily negative. How so? Watch this. Okay. Let's say the velocity is 2 meters per second. And in 5 seconds, it goes to 7 meters per second. Okay. So in what direction is the object moving? So you'll see that the velocity here is positive and also here it is positive. So the object is moving along the positive x-axis. How do I know? Because velocity is defined as delta x over delta t. Delta x is xf minus xi. For delta t, I'm writing just t. If this number here is positive, that means xf has to be greater than xi. Okay, my pen is a bit miscalibrated. So that means xf is greater than xi. Only then you will get positive value of 7. So that means this vf, it is positive. And also vi, initial value of velocity is 2, which is again a positive number, which tells you that xf is greater than xi. Even initially, it is moving in the positive direction. So in this case, it has also sped up, right? Now, what is the value of acceleration here? Delta v divided by delta t. Delta v is going to be 7 meters per second minus 2 meters per second. Final velocity minus initial velocity divided by time taken, 5 seconds. So this is going to be equal to 1 meter per second squared. Its sign is positive. When you don't write any sign, any algebraic sign in front of this number, positive is implied. And it should be because the object is moving, velocity is positive, right? Object is moving along the positive x-axis and it is speeding up. Therefore, this object that is moving along the positive x-axis that is speeding up must be pushed. Something is pushing it. It is pushed along positive x-axis. Only then it will speed up, right? Now push is what? Push is kind of a force. What is force equal to? Newton's second law that we have not done yet says that force equals mass times acceleration. Mass is a scalar, acceleration is a vector, force is a vector. So if force is acting along the positive x-axis, so is A. So we see here that acceleration and velocity are both positive. When velocity is positive and acceleration is positive, result is speed up. Okay? Let's see something else. Let me get a slide. Let's now say Vi is equal to 10 meters per second. And after 5 seconds, Vf is equal to 2 meters per second. 5 seconds passed. So in this case, velocity is still positive. If velocity is positive, that means it is moving along positive x-axis. So the whole way, it is moving along the positive x-axis. What is the value of acceleration? Acceleration is delta V over delta t. Vf is 2 meters per second. Vi is 10 meters per second. And time t is 5 seconds. So we get minus 8 divided by 5 meters per second squared. So in this case, acceleration is negative and it did slow down. So we say that velocity is positive, it is slowing down. So acceleration is negative. Now think about it. The object is moving along the positive x-axis and it's slowing down. That means a force has to be pushing it along the negative x-axis. So this force, which is equal to mass times acceleration from Newton's second law, it says that the acceleration has to be along the negative direction, along the negative x-axis. And in this case, this acceleration is indeed deceleration, and it is negative. We're not done yet. Watch this other example. Let's say an object is starting with an initial velocity of minus 5 meters per second. And after 10 seconds passed, the final velocity was minus 15 meters per second. Now we see that the object is moving along which direction? Positive x or negative x? Obviously negative x. Why? Because of this negative sign. This negative sign tells us that the object is moving along the negative x-axis. Okay. Here's the question. Sure, the object is moving along the negative x-axis. Is it speeding up or is it slowing down? So let's see. The speed of the object. Speed we know as the magnitude of velocity. So its initial speed, called SI, is 5 meters per second. Final speed is 15 meters per second. It's sped up. Correct? So the object is moving along the negative x-axis and it is speeding up. Let's now figure out the acceleration of this object. Acceleration, as before, is Vf minus Vi divided by Tf minus Ti. Okay, Vf is minus 15, all right? Vi is minus 5 divided by 5, not 5. Final time is 10 seconds, initial time is 0 seconds. And at the top, we're going to have meters per second. At the bottom, we'll have seconds. What do we get? Minus 15. These two minuses make a positive. It makes negative 10 divided by 10 meters per second squared. Minus 1 meter per second squared. So here we have negative acceleration, but it is causing the object to speed up. Would you call this negative acceleration as deceleration or retardation? Absolutely not. Even though this is negative acceleration, this is not deceleration. Do you see that? Let me give you another example. Let's say the object, it begins with velocity of minus 15 meters per second. I'm going to keep numbers the same just switch them around. After 10 seconds, it has velocity of minus 5 meters per second. See, as compared to the previous slide, where it began with negative 5 and ended up with minus 15. Here we are beginning with minus 15 and ending with minus 5 meters per second. So, like we said before, speed is magnitude of velocity. So initial speed is 15 meters per second. Final speed is 5 meters per second. Did it speed up or did it slow down? It slowed down. Okay. And what direction is it moving in? It is moving in negative direction. What is its acceleration? Acceleration is Vf, which is minus 5 meters per second, minus Vi, which is minus 15 meters per second, divided by 10 seconds minus 0 seconds. What do we get? We get 1 meter per second square. So here you see, here it slowed down. That means it is deceleration. However, it's a positive acceleration. So it is deceleration, but positive. Deceleration means only and only slowing down. Let's recap what we just did. Let's create a chart that's relating the direction of motion to speeding up or slowing down to acceleration. Let's say an object is moving along the positive x direction. So here, the object is moving along the positive x direction. And it is speeding up. So up arrow means it is speeding up. If it is speeding up while going along the positive x direction, that means a force is pushing it along the positive x direction. So here, a force is pushing it. Now force equals mass times acceleration. That means acceleration is along the positive x-axis. So acceleration is positive. Consider another scenario where the object is still moving along the positive x direction, but now it is going to be slowing down. If it is slowing down, that means the force is pushing it along the negative x direction. So if the force is along the negative x direction, that means the acceleration is along the negative x direction. Okay. Next, let's see an object that's moving along the negative direction here. It's going along the negative x-axis, but the speed is going to increase. It is speeding up. That means the force is pushing it along the negative x direction. That means acceleration is going to be along the negative x direction. Let's think of another example where the object is going along the negative x direction here, but it is going to slow down. If it is slowing down, that means force is pushing it along the positive x direction. That causes the speed to slow down. But the acceleration is along the positive x-axis. So here you see, it is speeding up, positive a, slowing down, negative a. So sure, this is deceleration here. And it is negative and it is slowing down. No problem with this. Problem is over here. Here, it is negative acceleration, but it is speeding up. It is not deceleration. It is acceleration here, right? Over here, in this case though, it is slowing down, but it is positive acceleration. So even though it is positive acceleration, it is still deceleration or retardation. So all I'm trying to tell you is that retardation or deceleration doesn't always mean negative acceleration. All it means is that slowing down. It can be moving in the positive direction or negative direction. It could have acceleration in the positive direction or negative direction and still be slowing down and still be speeding up. Hope this made sense. That's something that plays with the mind of a lot of kids. All right, acceleration due to gravity. So we know that every object that has mass attracts every other object that has mass toward its center of mass with a force called as force of gravity. Okay, so let's say on the surface of Earth, I know this is a very horrible looking Earth, you toss a ball up in the air. Is it going to continue to go up forever? No. You know that as it goes up, it's going to slow down. Why does it slow down? Because there's a pull toward the center of the earth. That pull is the pull of gravity. That pull slows it down. And it's going to keep slowing down until it reaches its maximum height. At that maximum height, the ball is going to stop. And then it's going to start falling back down. As it falls down, it speeds up, right? So this force of gravity that's causing an upward going object to slow down and downward coming object to speed up. This force of gravity is equal to mass times acceleration as per Newton's second law. However, in this case, this acceleration is a special kind of acceleration called as acceleration due to gravity. And we denote it by lowercase g. Like I said before, physics and chemistry, they are very case sensitive subjects. So this lowercase g, this is acceleration due to gravity. Or you can call this as gravitational acceleration. ACC dot is acceleration. This lowercase g and uppercase g, they are not identical. Uppercase g is called as universal gravitational constant. Its value is same everywhere in the universe. However, the value of lowercase g, it will vary even on a given planet. As you go away from the planet, the value of acceleration due to gravity goes down. As you come toward the surface of the planet, it increases, attains its maximum value at the surface, and if you start going into the planet, it again falls down, it again lowers. Okay, now let's talk about acceleration due to gravity on the surface of Earth. G on Earth. What is its value? Do you all know it? I bet you do. 9.81 meters per second square. Let's approximate it with 10 meters per second square. So we saw earlier that this meters per second square is actually 10 meters per second per second. What it means is that this is delta V over time. So what it means is that every second, the speed or the velocity changes by 10 meters per second. Going up, object will lose or slow down by 9.81 meters per second every second. Every second it will lose a speed of 9.81 meters per second going up. Going down, object will speed up by 9.81 meters per second every second. Let's look at an example. Let's say you drop an object on the surface of Earth. You drop it from rest. After 1 second passes, what would be its speed? Let's approximate the acceleration due to gravity by 10. So after 1 second has passed, it would have gained a speed of 10 meters per second. It speeds up by 10 meters per second every second. So 1 second later, its speed is 10 meters per second. Another second passes, that is 2 seconds from the beginning. Now it is 20 meters per second. 3 seconds from the beginning. Now it's going to be going at 30 meters per second. Okay, 2 seconds. Another second passes, total of 4 seconds. Now it's going at 40 meters per second. Another 1 second passes. 5 seconds from the beginning. So these numbers of time, these are from this point over here, 0 point. 50 meters per second, and so on. Now, if you want to be technically correct, instead of 10, use 9.81. Instead of 10, you will say it is 9.81 meters per second. It is 19.62 meters per second. After that, I don't want to do math in my head. So I'm going to get myself a calculator. I promise I can do this addition. I just don't feel like doing it. 19.62 plus what? 9.81. 29.43. Okay. Let's not forget meters per second. Add another 9.81 to it. 39.24 meters per second. Add another 9.81 to it and you get 49.05 meters per second. So this will be its speed at the end of 5 minutes. Let's not talk about another scenario where you toss the ball up with the speed of 70 meters per second. What will be its speed 1 second later? I'm going to call GS 9.81. Nah, I'm going to call it 10. Let's call it 10. 10 meters per second. 60 meters per second. Another 1 second passes. 50 meters per second. Another 1 second passes. 40 meters per second. Another 1 second passes. 30 meters per second. Another 1 second passes. 20 meters per second. Another 1 second passes. 10 meters per second. Another 1 second passes. 0. So how many seconds have passed? 1, 2, 3, 4, 5, 6, 7. 7 seconds. Now, of course, if you had taken G to be 9.81, it would have taken slightly more than 7 seconds. But then, we have ignored air resistance. For almost all of these problems, we are going to ignore air resistance unless otherwise specified. Okay, next thing. What are we doing next? Let's see. All right, so it's a recap. We already talked about distance. It's sum of all the path lengths. What is it? Is it a scalar or a vector? It's a scalar. And what are its SI units? Meters. All right. So that is our distance. Then we have what? We have displacement. Shortest straight line between initial and, okay, XI. Between initial position and final position. Is it a scalar or a vector? It is a vector. What are its SI units? Meters. Okay. Next we have speed. Speed is equal to distance divided by time. What kind of quantity is it? Is it scalar or vector? Scalar divided by scalar is a scalar. SI units, meters divided by seconds. And let's not forget that speed is also magnitude of velocity. All right. Next we have velocity. Velocity is displacement divided by what? Time taken. Is it a scalar or a vector? Meters per second. Now one more thing. Okay. Then we have acceleration, which is change in velocity divided by change in time. And what kind of quantity is that? Vector. What are its SI units? Meters per second square. All right, here's a new quantity for you, jerk. What a jerk. Not. It is change in acceleration divided by change in time. Its SI units will be meters per cubic second. Last, we're going to look at the inequality. We said that distance is going to be always what? Greater than or equal to displacement. And we also said that speed is always going to be greater than or equal to velocity. Okay, so this was a recap of what we have done. Motion in one dimension can be categorized as either uniform or non-uniform motion. Uniform, as the name tells, it is blue skirt, white shirt, yellow tie, red socks, silver shoe in one foot, golden shoe in the other. Absolutely not, though that would be fun. Here, uniform means constant. Constant what? Constant velocity. Now, we know that velocity is what? It's a vector quantity. Therefore, constant velocity means constant speed, because the magnitude of velocity is speed. Constant speed and also constant direction. So if velocity is constant, that is delta v equals 0, then acceleration, which is delta v divided by delta t, that's going to be 0. Therefore, acceleration for uniform motion is 0. Now, non-uniform motion, on the other hand, it means variable velocity. Variable velocity means acceleration is non-zero. Let's look at the details of non-uniform one-dimensional motion. We said that non-uniform means what? Variable velocity. If the velocity is variable, velocity is changing, that means delta v, which is vf minus vi, that is not equal to 0. And if delta v is not equal to 0, that means acceleration is not equal to 0. Okay, so variable velocity implies that acceleration is not equal to 0. If acceleration is not equal to 0, then it could be a non-zero constant or it could be a variable acceleration. In this lecture, in a few slides, we're going to look at a few equations of motion that are applicable to one-dimensional uniform acceleration motion. Before we get to that, let's look at variable acceleration in detail. Now, if acceleration is variable, it could be just a random variable. That means at 1 second, it is 10. Other second, it is 2. Next second, maybe it's 6. Whatever, it's just randomly just going whichever direction. Kind of like our Brownian motion. But in other cases, this acceleration, it can be a function of some other variable. Some other variable of what? Some other variable of the one-dimensional motion. Now, what kind of variables, which variables are involved in one-dimensional motion? We have initial velocity, final velocity. We have displacement and time. So what we're saying is that acceleration could be a function of velocity, acceleration could be a function of displacement, or it could be a function of time, or it could be a totally random variable. So we're not going to worry about this random variable. We're going to look at how to solve for equations when acceleration is a function of velocity, displacement, or time. So here we have non-uniform motion, which means that variable velocity, which in turn implies acceleration is non-zero. A non-zero acceleration could be a constant acceleration or a variable acceleration. Constant acceleration, well, name implies it is constant. Let's now look at the equations of motion for one-dimensional constant acceleration. Now, I'm in habit of calling it as one-dimensional uniform acceleration, just 1 DUA. So you may hear me calling it as 1 DUA. That just means one-dimensional constant acceleration. Okay, first formula for one-dimensional constant acceleration. Final velocity equals initial velocity plus acceleration times time. Now, look at this. We defined acceleration to be what? Vf minus Vi divided by Tf minus Ti. Let's call this Ti to be 0. That's when we're starting our stopwatch. And Tf is just T. So what do we get? Vf minus Vi over T. That means acceleration equals Vf minus Vi over T. Go ahead and multiply both sides by T. This cancels out the T in the denominator on the right hand side. What does this give us? This gives us AT, TA equals AT equals Vf minus Vi. Now go ahead and add Vi to both sides. What does this give you? Vi cancels on the right hand side. This Vf, bring it on the left hand side. Just swap left and right. This gives you Vf equals Vi plus AT. So here's your first equation of motion. It comes simply from the equation for the formula for the acceleration. Next, Vf squared equals Vi squared plus 2a delta x. Now how does this come? Let's see. We're going to derive this in just a few minutes. Okay. We'll derive it soon. All right. Last equation. Delta x equals Vit plus 1/2 at squared. And then we have the average velocity equals Vi plus Vf over 2. Now remember, these equations hold true only when the acceleration is constant. If the acceleration is not constant, then you're going to see that the equations are going to vary. How? We're going to look at those in a second. But before that, once again, we're looking at the equations for what? One-dimensional uniform acceleration, which I call as what? 1DUA. Okay. Very first equation, Vf equals Vi plus AT. Now, you may have seen this written as V equals V naught plus AT, or V equals U plus AT. They all mean the same thing. In this one here, V is final velocity, V naught is initial velocity. Here V is again final velocity and U is initial velocity. All right. Moving on. Then we have what? We have Vf squared equals Vi squared plus 2a delta x. This can be written as V squared equals V naught squared plus 2a delta x, or V squared equals U squared plus 2as. These are some of the common ways in which these equations can be written, in addition to writing it this way. Okay. Then we have delta x equals Vit plus 1/2 at squared. Of course, you can write this as delta x equals V naught t plus 1/2 at squared, or s equals ut plus 1/2 at squared. Last, average velocity. V bar, average velocity equals V plus V naught divided by 2, or average velocity equals V plus U divided by 2. Now remember, these equations hold true only and only when the acceleration is constant. Okay, what do we have next? Come on. So very quickly, I'm going to write these equations. V equals V naught plus AT, V squared equals V naught squared plus 2a delta x equals V naught t plus 1/2 at squared. How many different variables do we have? We have V, the final velocity, V naught, initial velocity, A, acceleration, T, time, delta x. Okay. So we have total of 5 variables. And we have how many equations? We have 3 equations. To solve for these equations, you need to know a minimum of what? You need to know a minimum of 3 variables. These need to be known. Only then you can solve for the remaining 2. Now the problems of this we're going to do in a later chapter. The next lecture after this will be devoted to motion graphs. And once I've finished the chapter on motion graphs, Then I'm going to begin solving problems of this chapter and of motion graphs. Okay, so now we know that in one-dimensional uniform acceleration, we have three equations, total of 5 unknowns. You need to know at least the value of 3 of these variables to be solved for the remaining 2. Okay, now moving on, if you have variable acceleration, that is a function of time, which can mean you have acceleration equal to, let's say it is t squared, okay? So if acceleration is t squared, it's a quadratic function of time, then the units here will need to be what? Here we go. So for example, if you have an equation like this, then in this case, let's say if you have an equation like this, let's suppress units here, okay? So units are implied. This 3 here, it is not just a constant number. It does have units. It has units of meter divided by second to the power 4. Okay. Now in this case, how do you solve problems? In this case, let's see. An equation. Let's get an equation for velocity here. Okay. How do you do that? How do we do that? We know that acceleration equals dv over dt. And now this acceleration, it's a function of time. So go ahead and multiply both sides by what? dt. And then take integral on both sides, where you're going from, all right, on the right hand side, from initial velocity vi to final velocity vf. And on the left hand side, you're going from ti to tf. What does this give us? Left hand side remains itself at dt ti tf, and integral of dv becomes v, going from vi to vf. Okay, so I'm going to have to bring it over here now. The right hand side, this gives you vf minus vi equals ti tf at dt. So here we go. We got an expression for velocity. When the acceleration, it's a function of time. Now, if you want, you could plug in the value of at over here. Right, let's go ahead and solve it. We have vf minus vi equals ti to tf 3t squared dt. Now, this 3, it's a constant. It comes out of the integration sign. Ti to tf of t squared dt. What does this give you? This gives you 3 t cubed over 3, going from ti to tf. Now remember, this 3 is not just a number. It has these units with it as well. So it is 3 meter divided by second to the power 4. Now this 3 cancels out this 3, and we're left with t to the power 3, ti to tf, and outside I have units of meters to the power seconds, meter divided by seconds to the power 4. Now look at this, t cubed. What would be the units of t cubed? It will be in second cubed times this meter divided by second to the power 4. So second cubed cancels out 3 powers up here. You're left with meters per second, as you should have, because on the left hand side I have velocity. So what we have gotten is vf minus vi equals tf minus ti, but the units here are going to be meters per second. So don't be fooled by this tf minus ti and thinking that how come I have meter per second on the left hand side and seconds on the right hand side. Right now, the way I have written this tf minus ti, this doesn't have any unit. The unit has been factored out, and it is meters per second. Next, variable acceleration, where acceleration is a function of position. So we have this acceleration as a function of position equals dv over dt. Okay. Now the way it is written, if I have to solve for the expression for v, I can't do it because acceleration here, it's a function of what? Position. So what I'll have to do is I'll have to use chain rule here. I'm going to write this as dv over dx times dx over dt. These are identical. Now dx over dt, it is actually velocity. So here velocity. So what I have now is a of x equals v dv over dx. Now go ahead and just like before, multiply both sides by dx. What does this give you? Ax dx equals v dv. Now go ahead and integrate both sides. Left hand side going from xi to xf and right hand side going from vi to vf. I'm not going to solve any problem on variable acceleration, where acceleration is a function of time or position or velocity in this lecture, but I promise we're going to solve several examples in upcoming lectures. Before we call it a day for today, let's look at this last topic, variable acceleration. In this case, acceleration is a function of velocity. We know that A acceleration is dv over dt. Okay. So what I'm going to do here is go ahead and multiply both sides by dv. So I'm going to multiply both sides by dt. And then I'm going to divide both sides by a of v. What does this give me? This gives me dt on the left hand side, and on the right hand side the dt cancels out. I'm left with the dv divided by a of v. Alright, that's a poor v. Let's fix it. Okay. Now why did I do this? I have pulled a of v to the right hand side so I could integrate it. Okay. So ti to tf on the left hand side, vi to vf on the right hand side. Now all you need to do is plug in the expression for a of v and you can solve for your v. Alright, so these were the topics for today. Very quickly, what did we do today? We are working on motion in one dimension, and we looked at several definitions. For example, kinematics. What did we say? Kinematics is the branch of physics that deals only with how of motion, not with why of motion. And we said that dynamics is the branch of physics that deals with why of motion, which is the different forces that are acting on the objects and how they cause motion. After that, what we looked at was point object, and in what cases can we treat an object as a point object. Then we moved on to defining distance, displacement, speed, velocity, and acceleration. And we said that distance is always going to be greater than or equal to displacement. And we also said that speed is always going to be equal to or greater than velocity. And we also said that speed is magnitude of velocity. Okay. Then we talked about deceleration or retardation in detail. And we emphasized that deceleration doesn't necessarily mean negative direction. You could have deceleration and have it in positive direction. Deceleration or retardation has only one meaning, and that is slowing down. Then we looked at four formulae, which were V equals V naught plus AT, or you can say VF equals VI plus AT, V squared equals V naught squared plus 2A delta X equals V naught T plus 1/2 AT squared. And lastly, we said the average velocity for one-dimensional uniform acceleration is V final velocity plus initial divided by 2. Then we looked at cases where acceleration is variable, it's not uniform, and it's a function of either x or t or v. And we looked at how to obtain an expression for velocity in these different cases. So that was this for this lecture. I hope that it was useful for you, and I'm assuming that if you made it this far, then you found it useful. If you found it useful, please do hit that like button and subscribe to the channel. It means a lot to me. Next lecture will be coming up soon, and it will be on motion graphs. I'll see you again very soon. Until then, have a good one.